Hello everyone and welcome to the solutions video for Codeforces Round 779. I'll be explaining for A to D1. They were pretty simple I think, but C was very easy to mess up and I'll tell you why. But with that said, let's begin discussing the solutions from A to D1. And before that, make sure you have subscribed. Let's go. I haven't opened this. Cool. What is this? No one cares. Okay, problem A. Okay, in this problem, there are, okay, so there's this queue of people where 0 means a boy and 1 means a girl. So it is something like this, right? And what we want is we want that for any substring of this string, the number of boys should not be greater than number of girls. So number of girls can be greater than number of boys, but number of boys should not be. All right, so let's start with subarrays of size 2. So for subarrays of size 2, because we have to check for only subarrays of size greater than equals to 2, because it wouldn't make any sense for subarray of size 1. All right, let me just move it over here. No problem. Yeah, so when two boys are adjacent, obviously I'm gonna need one girl to be between them. So if it is like this, then these substrings are all right, but this entire substring will still have two boys, which is greater than 1, which we don't want. So I'm gonna have to do it like this. So for every adjacent pair of boys, the number of girls to be added has to be 2, and then obviously for anything bigger, if there is some ones over here, it doesn't matter. However, there's another thing you have to worry about is this type of pattern. So if there's only one girl between two boys, I'm gonna need two girls as well. So essentially what I need is a number of boys to every 0, or which is a boy, to not be adjacent to any other 0, and also the distance between every adjacent to be greater than equals to 2. So there are multiple ways to implement it. I implemented it like normal, just like I explained the two cases. So this is the first case where I'm checking adjacent zeros. In that case, I add 2 ones in between, and if there is, it is like this, 0 1 0, then I add 1 1, so answer plus plus, and then print it. So pretty simple. And okay, so let's move on to the next problem, problem B. So in this problem we want beautiful permutation. So a permutation of 1 to 5 is like reordering of this array, right? So we want to reorder this array. Let's say it's like 3 4 2 1 5, and now we multiply each of them by its position. So this gets multiplied by multiplied by 1, multiplied by 2, 3 4 5, and then the final array that we have is 4 25, and what we want is the GCD of this to be greater than 1. Okay, so how can we get this? Well, let's try to see if we can get some big GCD possible. Let's say if I wanted a GCD of 5, so let's say the array was pretty big and I want GCD of 5. So for the first 4 elements, I'm gonna need multiples of 5, right? And then in the next one, I can have anything from 1 to 4. And then again, I'm gonna require multiples of 5, and then some non-multiple of 5. So you notice that because obviously the non-multiples of 5 are more than the multiples of 5, this would not fit. We won't get every number to be divisible by 5. And same logic applies to 3, 4, 5, and so on, except for 2. And even for 2, it's only possible. So let's take this example, right? Let's say we have an array where there are 7 elements, right? If we want GCD to be 2, then let's have 1 2 3 4 5 6 7, At even positions, I'm gonna put odd numbers because then they would become even anyways. And then at the odd positions, I'm gonna put the even numbers because they are even, never mind anyways, right? So, but when n is odd, I'm gonna require 8 to be here, which is not in it. So even when, so even for, you know, n GCD equals to 2, we are gonna want the length of array to be divisible by 2, because if it is divisible by 2, if 7 was not there, right, if 7 was not there, then it could have been just like this. So you can get one of the good permutations by just swapping elements like this, and this way we'll make sure that at odd positions we have numbers that are even, and at even positions we have numbers that are, and so everyone will have some factor too. Okay, so we just have to worry about when n modulo 2 is equals to 0, and when in that we only care about GCD2 because others are impossible. And we know that odd numbers have to go into the even positions and even numbers have to go into the odd positions, and all these positions are equals to n by 2. So number of ways to arrange n by 2 numbers in n by 2 positions is just n by 2 factorial, and this happens separately for odd and even positions. So by basic counting we get this value, right? So this is the number of ways to place odd numbers at even positions, and this is the number of ways to place even numbers at odd positions. So many ways to implement it. You don't need to do any pre-computation here because n is just 1e3, but I had done pre-computation because I thought I'm gonna need NCR. Anyways, we just take n. If it is modulus 2, we get a remainder, then answer is 0. Otherwise, answer is factorial of n by 2 multiplied by factorial of n by 2. You can calculate it in linear time here as well because n times 3 is still 1e6. Okay, then problem C. This is a pretty bad problem in my opinion. I mean, rather than bad, I would say it is tough to properly do. So okay, what do we have here? Here we have a permutation again. So let's say 3 4 2 1 5, and an ith cyclic shift just means that ith rotations to the right. So if I do 2 cyclic shift, then it becomes 5 1 5 3 4 2. Okay, so rotate to the right twice. So this is the operation that is being done on this array, and after doing this operation, so we had a permutation initially 3 4 2 and 5, and this right cyclic shift is done n minus 1 times, and we are given what is the number of unique values in the prefix maximum of this array. So initially, what is the prefix maximum of this array? It is 3 4 4 4 5. So number of unique elements in this is 3. Then after one cyclic shift, the array is like this: 3 4 2 1 5, 2 1, and the number of unique elements is just 1. Then after one more shift, it is like this. So we are given up to the last point, so that would be 4 2 1 5 3. So the last rotation, and that is 4 5, right? These would be 4 and these would be 5. And so we want to tell if these values that we are given, what we are given, the number of unique elements in the prefix maximum after every cyclic shift, if that is consistent with any possible permutation. So if that is a valid operations, if that those are a valid sequence after these operations. Okay, so how can we do that? Well, let's assume that when we had something like this, right? So for this we had prefix maximum 3, for this we had prefix maximum 4, for this we had prefix maximum 5. So prefix maximums are something like this. So initially we have some value C0, right? So the first element of this is equals to C0. Sorry, the number, this is C0, right? 3, C0 equals to 3 because there are 3 blocks of different prefix sums, and the first element here is bigger than all these. The first is here is bigger than them and them, and then this is bigger than all of these and these. Okay, so it is something like this. Now let's see what we can figure out in this. Well, when we do one right cyclic shift, what can happen? Let's assume that the element that is moving was not the biggest element, which was here. So let's say it was some 3. So if it moves over here, multiple things can happen. This 3 can either be smallest element, and so smaller than like this 4, 5, and maybe 7, right? Let's call it 6 and let's call it 9. So it can be smaller than everything, and then the number of blocks would be would become one more. However, it could also be like 5. So if it is 5, then it nullifies this and the number of blocks remains same. It could also be like 7, and hence it nullifies this as well. So number of blocks can decrease as well. And it could be like 10, bigger than everything. So number of blocks can decrease as much as possible, up to like, it can become 1 when the biggest element moves to the left, right? So in one cyclic shift, the number of elements, the number of unique elements in the prefix maximum can increase by 1 at best, or they can decrease by some amount. We don't know, we don't care, for now at least. So that is one constraint we have to make sure that the array is, what we say, valid, right? So now let's consider what happens when the biggest element moves to the left. When the biggest element moves to the left, then everything becomes part of that element's block. So this is like n, everything is there. Prefix max would be like this, right? And so in this case, the number of elements would become 1 in the prefix maximum, of course. And so this happens whenever the biggest element moves to the left, and this will surely happen when we are doing n rotations, right? So since this will always happen, we can be sure that one will occur somewhere in the array. So some ci has to be equals to 1, and that will only happen once because no other value will overpower this. So count ci equals to 1 has to be also equals to 1. And also what also happens is that when yeah, pretty much that is it, right? Because ci has to be 1, and then after that we can have similar pattern. So the constraint was that the value of ci can increase by only 1, or it can decrease. So it could be like 2, 3, it can remain 3 as well, like maybe it drops down to 2 again, then 3, then 4, then 5, then 2, and so on. But remember that after the last one, if we rotate once more, we will go back here only, right? So that means that the constraints that we came up with should be followed in a cyclic pattern. So after 2, it has to be 1. So it cannot be like something like this. So it is, let's say 3, 4, 5, 1, 2, 1, 2. Let's say what, 4, 4. Okay. So if it is like this, we see that okay, the delta is always less than equals to 1, and and 1 occurs only once. So it seems good, but notice that after this the delta is 2, so we have to take care of this as well. And these are the only two required conditions. I had some extra conditions in place due to which I did not AC in the contest, my bad, but that's about it. So delta has to always be less than equals to 1. If it is ever greater than 1, then print no. And see, I'm going from 1 to n so that I'm also checking this last pair, and then I'm finding the number of ones there are. I was also storing position, but they were for different checks. Don't worry about that. So if the number of ones is not 1, then also print no, otherwise it is always possible. So it's really hard to convince yourself that this much is enough, and that is why I think it is a very hard question to properly solve. And this is just me coping, I guess. Okay, so let's look at this problem. So here, what happens is this person Gojo chooses a range L to R. Okay, and so he gets an array like this, which is R here, and then he chooses an element X and calculates L XOR X, L plus 1 XOR X, and so on, R XOR X. And we are given this new array, right? This is A1, A2, AN, where N is equals to R minus L plus 1. So we are given this array. We are also given L and R, and we want to tell what X was chosen. And also after this it was shuffled. So a permutation of this has been operated on, not exactly L to R, because then we can trivially find it. So we want to find what any one valid X. Okay, so let's see. Because it is a bitwise related operation, checking it from bits will be very useful. So let's see. Let's say for the 5th bit, there are 10 elements that have this on in the permutation of L to R, and let's say there are 15 elements in this, right? So if 10 of them has this bit turned on, and so 5 of them would have it turned off. So now, depending on if X has that bit turned on or off, if it has that bit turned off, then what happens is that in the final array, for 5th bit in A1 to AN, the number of bits, the number of times 5th bit is turned on would remain 10, because in X it was 0. So 1 or 0 is 0. 1, right? And so number of unturned bits would obviously be 5, and which is 15 minus 10. However, if this value was equals to 5, so that means, okay, let me do it in a tabular form. So this is our original range or the elements, and this is our new elements. So let's say turned on and turned off for any specific ith bit. If there are, let's say, 10 bits turned on and 5 turned off, then there are only 2 possible cases. Either it would be the same configuration. In this case, xi, that is ith bit of X, would be 0, or it would be the opposite, because in that case this would be 1, because XOR inverts the bit. So for every 0 it will turn it to be 1, and for every 1 it will turn it to be 0, right? So this happens, and so this way we can trivially figure out which bit would be turned on and which would be turned off in X, and then we can get the answer. However, there is a catch. What if let me just erase. What if this was 5, this was 5? Then if this is 5 and this is 5, we have no idea whether we want to turn on this bit or turn off this bit. And I'm back. Sorry for the pause. But where were we? Yeah, so when the bits for 1 and 0 are same, well, in this case, because L starts from 0, this does not matter. I don't have a concrete proof for that. If I get it, I will post it in the comments. And also, that was the easy part of this problem. So in these cases, you can also try, guessing that maybe that would work out. I mean, I do not endorse guessing, but if you have no time and also no hope, then you can try. And then problem D2, I did not solve it, so I won't be discussing it. But before that, let's see the solution for D1. So mod plus, okay. So yeah, I have a vector A. Yeah, so I have a vector A, I take the input, and then I have count 1, which is the original count. So for L to R, and count 2, which is the count for array A, and this represents the bit number. So I add so I get the counts of every bit for every number. And now for every bit, if the counts are not equal, then there's just an assert that the other part of the count, that is n minus count 1, has to be equal to count 2. They have to be complementary, right? And if that is the case, answer or equals to this. And then I just did a sanity check and had added an assert, and then in the end print answer. Obviously this assert would fail if L is not equals to 0, but that was for D2. And so yeah, these were the solutions for problem A to D1. If I get this proof for this little hypothesis I said, that if L is equals to, that due to L equals to 0, them being equal does not really matter, I will post it in the comments. And with that said, hope you guys found this useful. If you didn't, I'm sorry, I'm performing really bad these days. What can I do? Maybe I can practice a little bit. But yeah, with that said, please leave a like, subscribe, and I'll see you next time. Bye.